let's have a little play with enthalpies and energy diagram. And we're going to be looking at enthalpies of formation. An enthalpy of formation, a standard enthalpy of formation, and it's called delta FH0, and 0 represents the standard conditions, which is that the compound is in its pure form with 1 bar of pressure at 25 degrees, nominally room temperature. And so a standard enthalpy formation of a chemical is the changing enthalpy for the reaction that forms 1 mole of that compound from its element. And the elements, all those elements, will be in their standard states at 25 degrees. And the standard states are defined, yes, at 1 bar and 25 degrees, but in a particular way. Like, for example, how you make carbon, how you make CO2 gas. Well, in a standard enthalpy formation, well, you will make it from the elements in their standard states, and the standard state of carbon, of the reagents to make CO2 would be carbon and oxygen, the molecule O2. So you've got carbon and oxygen, that will give you CO2. And CO2 is gas because it's a kind of a normal form. Oxygen in nature is as a gas, the gas O2, and carbon carbon has several states. It could be a graphite, it could be a diamond, is defined as carbon graphite. So each element has a particular, and each chemical has a particular state that is considered like the normal one, what is called the standard state. And sometimes when you have a particular compound or a particular element like carbon that can have several forms, graphite, diamond, then you pick one of, the chemical, we chemists have picked one of them as, that is the standard state. We can use Hess's law and tables of standard changes in enthalpy of formation to calculate any standard enthalpy change we can think of. And when I call them a standard enthalpy change of any reaction I can think of, I mean a standard because it would be at 25 degrees, it would be a 1 atmosphere in pressure, 1 bar in pressure. So, what you call a standard conditions. So that was that's what the super zero means, standard conditions. So if we have the standard enthalpies of formation of all the chemicals involved in our reaction, in this case, we've got the combustion of propane, which involves propane gas, 5 moles of oxygen, also in gas form, to produce 3 moles of CO2 and 4 moles of water in liquid form. So if we have the enthalpies of formation of all those chemicals, that's the propane, the oxygen, the CO2, and the water, then we can calculate the enthalpy for this reaction as the sum of all the enthalpies of formation for the products to whichever coefficients we've got, like 1, 2, 3 moles of whatever product you've got, minus the sum, and we use that Greek letter, of all the enthalpies, the enthalpies of formation of all the reagents. And here you've got the example of the combustion of propane, and I'm giving you 3 reactions. I'm giving you the formation of propane gas, the formation of CO2 gas, and the formation of water liquid. So I'm giving you the formation of one of the reagents, the propane, and the 2 products, the CO2 and the water in liquid form. And the standard formation of oxygen as the standard formation of any element in its natural state is 0, because it's considered that its not form is already there. So the standard enthalpy of formation of oxygen gas, hydrogen gas, helium, nitrogen gas, an elemental phosphorus, an element in its elemental form, it's considered that the enthalpy, the standard enthalpy of formation is 0, that you don't have to form them, they are already formed. So if you have those 4 pieces of information, could I ask you to use all those enthalpies of formation to calculate what will be the enthalpy, the standard enthalpy of that reaction, propane and oxygen to produce CO2 gas and water liquid? Stop the video now, please. So I hope you stopped the video and had a good exercise. I decided that my handwriting in my computer, it was too messy to write this down by hand, so I prepared this slide with all the calculations. So what will be the enthalpy of this reaction, the standard enthalpy of the reaction? Well, will be the standard enthalpy of the products minus the standard enthalpy of the reagents. We know the standard enthalpy of formation of oxygen is 0, so that's 1 less to worry about. So what will be my products? My products are CO2 gas and and water liquid. 3 moles of CO2 gas and 4 moles of water liquid. So if I look at my equations of formation, I've got the one for the CO2 and the one for the water liquid. And I multiply 1 by 3 because I'm making 3 moles of CO2, and the one of water liquid by 4 because I'm making 4 moles of water. And then I look at the enthalpy of formation for propane, which is my reagent, and that one, because I have 1 mole of propane, that reaction requires 1 mole of propane, I don't need to multiply by anything because that reaction of formation already gives me, sorry, I brought it the other way around, it would have to be like this way. It already gives me 1 mole of propane, which is what I have. So when I put all my my equations, or all my information in my equation, I've got that I'm making 3 moles of CO2, and each mole of CO2 releases minus 383.5 kilojoules when it's made. And I've got my other product is water, and I've got 4 moles of the water. And then I have, so these are the products. This would be what we call the sum of the enthalpies of formation of the products minus, and this is the sum of the enthalpy of formation of the reagents. I've got 2 reagents, the propane and the oxygen. The oxygen, because it's in its elemental state, has an enthalpy of formation of 0, so we only look at the propane. So if I add up all this, the enthalpy of the reaction in standard conditions is minus 2,220 kilojoules. So this is an exothermic reaction, and it will release that amount of energy, and I can put it here. So what if I wanted to write that in an energy diagram? Well, we have already done this, and although it does look quite busy and complicated, it's just a way of showing in a graphical form all the bits of information that we show in previous slides in a sequential form. We've got the reagents, the propane and the oxygen, and the products. And this is the reaction we are interested on. And then we have different ways we might want to go about going from those reagents to the products. I mean, we could just literally mix propane and oxygen and make it react, and you will release CO2 and water. You could also think of, well, another way of doing it would be a decomposition reaction. So, which is what we had before. In this case, it was a formation reaction. You've got carbon, and you've got and you have hydrogen to make methane and carbon in the form of graphite, which is what we call the elemental state. And then we've got the formation of a CO2 by thinking of, okay, well, I could think of carbon and oxygen will give me CO2, And then you would think of, okay, well, I would have hydrogen and oxygen, that will make me water. So what I've done is I've drawn all those reactions I had before, and with the right coefficients, with the right number of, I need 3 moles, I produce 3 moles of CO2, I produce 4 moles of water. I've put it all in a diagrammatic form. And that's how we look, the energy diagram. And the point is that the reaction going this way from the reagents to the products, or going this way from the reagents to the products, the result is the same, because enthalpy is a state function, so it's only the starting and the end point that matter, not how you got there.